You are live. There you go.
Is it coming okay?
Yeah, just you need to switch into the full screen thing. However you did that. There you go. Yeah.
Oh, okay. So then,
at the bottom of your yeah, exactly. Oh, what happened there?
okay, I just had to go back. I want to remove the.
There you go.
I think it's better. Yeah.
Yeah, it's looking good.
All right. So we are continuing today from episode 1. You may have already seen these. Episode 1 was what led to the classical physics, the history of physics. Now we are continuing with that, and for details you can refer to episode 1. But we are continuing with what happened after Galileo, Newton, and all the universal mechanics. The next step was thermodynamics and electromagnetism, Maxwell equation. That's it. That is this episode. It talks about the conservation laws. Now we don't know exactly how that came into being, but essentially it was decided based on the mechanics. There has to be some sort of a conservation, and the conservation it could be mathematical also. That the conservation laws said that the energy has to be conserved and for a system to operate. And then it was also hinting at conservation of momentum. So because of transfer of energy as well as forces, things like that. So we'll go over that, what happened. The first one was thermodynamics. That talks about conforming energy conservation uh, laws. The very first law talks about that energy cannot be created or destroyed. It can only change forms or transfer from one system to another. So that formed the fundamental basis of all of the sciences. As we know, all of the physical sciences, especially physics and chemistry, as well as all of the forms of uses that aspect, because that then helps to predict things and things like that. This principle aligns with the broader conservation of energy that was seen to be observing throughout the universe. And as we see that Carnot cycle engine, etc., specific experiments through that, and later on, it was tested on many different situations and found to be true. Heat exchange and work done by our own system. The first law connects especially internal energy. So the concept of internal energy was very important, and the heat. Thermodynamics essentially talks about the heat transfer, things like that. So that's a form of energy that is being discussed in thermodynamics, and the work done on the system by or by the system. So the fundamental equation, one of the fundamental equation is the internal energy is equal to the heat added or removed minus the work done on or by the system. So suppose we have energy input, when heat is added to a system, we know that the Q has to be greater than 0. And in that case, the equation says the internal energy has to increase. So if you have energy output, which means that energy is done by the system, the W has to be greater than 0, and it will decrease the internal energy. So the net change in internal energy accounts for both heat transfer and work done. So we know that if the internal energy is changing, there has to be some sort of a transfer or work, things like that going on. So that we can figure out. For example, heating a gas, we use heaters in cold climates, things like that. When you heat a gas, also in a piston cylinder system, for example, in car system or internal combustion engine, things like that, internal energy increases due to the heat that is added. And adiabatic compression, for example, adiabatic is when the volume is constant no heat exchange occurs, and the work done on the gas increases internal energy. So we know the pressure increases. So adiabatic essentially means the whole volume of the system is held constant. So there is no transfer outside. It's not an open system. It's a closed system. Energy conservation engines, for example, heat engines, like in cars or any transport vehicles, transportation systems, we produce heat energy. For example, uh, through heating using a petroleum or a gas uh, that we ignite and then heat it up in a chamber, and that heat energy is transferred into mechanical work through the piston cylinder system. So it converts the heat energy to mechanical work. But that also, if you calculate that, that follows the first law of conservation. So the overall implication is that the first law ensures energy is conserved during any thermodynamic process. It guarantees the total energy within the closed system remains constant. So that's a very important information for us to figure out what's going on, the mechanism, or what's going on inside any system, or to develop systems or design systems. So historically, we are emphasizing on the historical aspects here of the physics. The foundations were based on, Carnot's original publication. The classical thermodynamics emerged between 1850 and 1860. So in the latter part of 18th century, somewhere middle part of the 18th century is where uh, it's actually developed because of the work of scientists such as Lord Kelvin, uh, Clausius, and Maxwell. So they are dependent on the work of Carnot, who had published in 1824 Reflexions or La Puissance. I'm not going to tell the whole word because I don't speak French, but or some other language. It could be Dutch, things like that. So essentially, that was the publication, which probably would be translated to English, and that laid groundwork for all of thermodynamics. So Carnot was one of the main architect of this thermodynamics unification concept. Uh, unified concepts relating heat, work, temperature, and see at that time of the industrial revolution, it's very very important, right? All fired furnaces making in metals are also heating systems, and also vehicles, transportation systems. Everything were developing at a rapid pace. So they need to understand how all this worked and also help in the design of better, heating systems or engines, things like that. And thermodynamics help to bridge the gap between heat engines, such as steam engine was the most popular form of uh, transportation, not only on land, but also especially on water. For example, all the boats or ships, things like that, were based on steam engines. And the know-how understanding of fundamental principles was quite important to understand how the transformations occur, especially with respect to energy. So the technological applications included steam engine, internal combustion engine, which was the primary aspect. Even now, in cars, in all the vehicles or transportation systems, electricity generation, as we know, from coal-fired furnaces, the electricity had been generated until the hydroelectric aspects came into being much later, little later. So they give insights also the design variables to design efficient engines and power plants uh, that form the crux of the application. So it also helped to develop the atomic theory. Uh, we will be talking episode 3 about that, but about structure of atom, which was developed later around that time. So they explored the behavior of matter, realized energy change is fundamentally related to behavior, individual atoms or molecules. At that time, we know from Dalton's theory that the smallest you know, element in a matter is the atom. So they know energy is being transferred between them. So that the thermodynamics help to understand what's going on. So the practical applications were for the thermodynamics, the classical thermodynamics that we call, is in heat engines, power plants, refrigeration, air conditioning, chemical reaction to understand quite a lot in chemical reactions. As we know, the Clausius-Capron as well as the you know Lee Chatelier principle, they all help to understand how the reactions move forward or backward, things like that, in a chemical reaction. So the set of uh, reactants acting to create products. So how that works is described by this thermochemical physics. And also equilibrium, how it keeps equilibrium in that system. So designing and optimizing heat engines that we talked about is steam engines, gas turbines, internal combustion engine, power plants that included later on nuclear, fossil fuel, which is petroleum products. We call in the US gas, uh, and then renewable energies that we are now interested more, like solar energy, things like that, converting heat energy to mechanical work or electricity. The operation of refrigerators, air conditioners, heat pumps, they all follow the environmental cycles of vapor compression cycle. For example, we know we use freons inside a refrigerator that goes through the vapor compression cycle and that keeps it going. And so we can use the refrigerator, which was quite important. And even now, every household has that. Then understanding phase transition, condensation, vapor, evaporation, essential of cooling and heating systems. So they go through these cycles of phase transitions. Uh, it also helps in the predicting feasibility of chemical reaction. So many other reactions that we are interested in, we want to produce a new product, chemical product. We have to know what are the reactants, including organic chemistry. They use we have on one side we have the reactants, on the other side the products. So you want to convert from one to another. For example, industrial process like a Haber Bosch process, ammonia systems, they used extensively, like how nitrogen, hydrogen combine to form ammonia. So we have to find out the pressure, temperature, volume aspects, and that's very well described by the thermodynamics, as well as the environmental chemistry that studied what's going on in atmospheric sciences. Okay, so the particle applications also included material science and metallurgy, which was one of my main focus for my graduate study, uh, and heat treatment process like annealing, quenching, and tempering rely on that. Phase diagrams, which describes what phases exist, including solid, liquid, gas, because that's important for extraction of uh, you know metals from the ores. So like iron oxide, things like that are there, and we have to separate the oxide to pull out iron from that, and also make steel and things like that. So they depend on the phase diagrams gives the whole quantitative way of doing that, and that depends on this thermodynamic aspect. Then thermal comfort and building design. Architects and engineers use them to design energy efficient building. Even now we know that windows, even including windows, things like that, uh, that it can leak cold air, things like that. So we have to how to make it efficient. Insulation, ventilation, and heating, cooling systems. Then we have high vacuum heating, ventilation, and air conditioning, optimize indoor comfort. And then we know that that's critical for some people than other people, especially in the in what zone we are living in. So they become quite important. Steam engines and gas turbines, power generation steam turbines like coal fired power plants and gas turbines. in aircraft engine power plant. They rely on that, and this was developed from the industrial revolution. It started, uh, going at a fast pace into these systems. Then chemical engineering process, distillation, extraction, separation process, based on phase equilibria. Again, like even petroleum industry, like talked about, you have all these processes going on. Uh, it also guides the process, optimization, efficiency, things like that. Environmental science, it helps model Earth energy pattern, climate change, atmospheric process. So what's going on in the atmosphere? What creates a cloud? What creates the evaporation from the sea, the water, then the forming cloud, and then we have the cloud. What type of cloud will condense to form rain, things like that. All these are studied by the thermodynamics that's going on, and also other uh, what you call the systems that's going on inside the sea, like vortices, things like that, and also formation of tsunami, even things like that. Uh, entropy. Entropy, I didn't mention. The second law talks about entropy. Again, I'm not going to detail about the technical aspects or science because that is a long, we have textbooks that cover that, courses that cover that. It's a long, uh, process that you have to go through to understand them and also apply them. So many people started, as we know, people were in general studies beforehand, but by the development of these processes, like the understanding each process, people start to be specialized in each area. So then there will be a person who is expert in thermodynamics, works solely on that and do research and publish on that. So we have lots on that. I also studied a fair amount of thermodynamics. And we know that entropy, the second law talks about entropy, keeps increasing in the universe. Uh, and actually, the time is related to that. Again, I'm going to detail about it, a lot of studies on that. We are also doing the studies uh, about how the entropy and energy is acting, like in sourcing mechanism, things like that. The heat transfer, essentially for understanding global warming. That's again a very controversial subject even now, but it may be important as we go along. Thermal analysis, quality control, thermogravimetric analysis, differential scanning, calorimetry. There are specific things that are used to understand material properties, to design uh, to make things better, and also to solve certain problems, like in even transportation systems, things like that, or at home appliances. They all come into picture. Quality control depends on the dynamic stability and phase transitions. So we use many things that uses even chemicals, things like that. So they have to be stable. They cannot release gases which are toxic. Uh, Also, the pressure conditions, even enclosures like gas cylinders, things like that. We have to know what's going on. Phase transitions that are kind of solid, liquid, gas, among other things. Even within the solid, there are phase transitions. So they all depend on thermodynamics. The biological systems and physiology, our own body systems, like metabolic process, enzyme kinetics, cellular transfer, what happens inside a cell, all that. Body temperature regulation, and we have to keep like 98.7 whatever our normal temperature. If it's that, we get fever. If it's too low, then we into trouble because our heart and all the systems uh, is well balanced, and the heat exchange and things like that very important. So if it's a very cold climate, then we need heaters, things like that. If it's a very hot climate, then we need air conditioning. So they all use thermodynamic principles. Okay, so now we talked very briefly about the history and specific aspects of the thermodynamics without going into details about the actual physics or mathematics. But now we move on to the next level of great achievement, development from classical physics. is the electromagnetic aspect based on what we call Maxwell equations, which unified electricity, magnetism, and light. So the Maxwell equations successfully unified different theories of electricity, magnetism, and light. And Richard Feynman, the famous Richard Feynman, the Nobel laureate in physics in recent history, um, quantum electrodynamics is what his main areas. But he said that he predicted Maxwell's discovery of the law would be the most significant event of 19th century. And all of it, that's the fundamental basis on which much of the physics is based on, especially the mathematical physics. The four Maxwell equations of the electromagnetism. Okay, he concentrated on electromagnetism, as we say. There are different forms of energy, but electromagnetism is one of the higher forms of energy, and he concentrated on understanding that. And it's based on Gauss' law of electricity. The first law the first equation was based on Gauss's law, which describes that electric fields originate from charge distribution. So Gauss said that all electric fields, charge is the fundamental basis on which electricity is based on, like electrons, for example. Mathematically, he said that of a closed plane area or surface area, the electric field has to be, enclosed, has to be described by the charge, the total charge, divided by the epsilon naught, which is the permittivity of vacuum. So again, I'm not going to detail. I'm just pointing out. Okay, the second law again is based on the Gauss law for magnetism. He says that there is no magnetic monopoles possible. That is a very important discovery of Gauss that is used to understand that in a closed system, the magnetic field around surface will have to be zero because no magnetic poles can exist. That's the fundamental law. The Faraday talked about induction, that the magnetic field changing magnetic field can induce electric field, changing electric field can induce magnetic field. So this was a very important, discovery, then it could lead to invention of, for example, electric motors, dynamos, and all that, generators, and things like that, among other things. Then he said that this is current through a wire, for example, electric field to a current, is connected with the change in the magnetic flux uh, through the surface. So that is very, very important law. That was the third one. Then Ampere's circuital law, it connected magnetic field to electric currents. But Maxwell also introduced a term to to come up with the right type of equation. So he found when he was doing the math or the quantification, he found that there's some term missing in that. So he called them displacement current based on the permittivity and also change in the electric field. So the changing electric field between, for example, he was studying capacitor plates. Um, so when you actually do write down the equations, he found that the magnetic field going around a wire, uh, you know, we have circular magnetic fields around the wire, and is connected with the electricity that's produced, like in transformers and other things. Uh, so it is connected with the permeability on mu naught times the I. So magnetic field is associated with the permeability, and the electric field is associated with permittivity. So then he said that there should be a term that's interactive, which means both permeability and the permittivity should come together. And then he discovered the idea of vacuum, where the speed of light is constant. Right? So mu naught directly connects with the speed of light. This is 1 over c squared, right? V naught mu naught. Uh, and then he said that that's based on because of the changing electric field. So that is an important discovery. Okay. So again, I have not gone to detail about that. So some aspects we are considering. But then we say Maxwell equation, how we converted the mathematics that he developed into the physics aspect. Uh, he could actually infer or interpret that standalone charges and currents, if they are even if they are absent, they that means the equations are homogeneous. They predict the existence of electromagnetic waves, including light. So the light can travel. So it has self-propulsion, self-propagating property. So that was a big discovery that it doesn't need an external force to move the light. Uh, it can self-propel itself. It has some energy within which is oscillating that it is transferring and it is transmitting and it's able to uh, go through space. So changing magnetic fields create, because he said that the changing magnetic fields create vortex-like electric fields, and changing electric fields create vortex-like magnetic field. So they go back and forth like cycle. And that coupled fields propagate as waves, even very far from the sources. They keep going. There's self-propulsion aspects, and they travel at the speed of light, especially in vacuum, constant speed of light. And this was, of course, uh, eventually this was supported by Michelson-Morley experiments, things like that, which measured the speed of light, and 3 to the power, and approximately 3 to the power 10 to the power 8, 3 times 10 to the power 8 meters per second. So this was the measurement that really made Maxwell equations stick. Uh, then he said that the Z waves consider oscillating electromagnetic fields that, so by this oscillation back and forth, so one convert to another convert to this, like this process continues the mechanism. And we are still trying to understand a lot of that. They found the basis for the propagation aspect of light. So then based on that, you could predict that about radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, as well as gamma rays, among other aspects. So the wave equation was really powerful to understand not only electromagnetics but also light, which he proved that is nothing but electromagnetic waves. So he combined the Faraday law and Ampere's law, and he could come up with the wave equation for electromagnetic fields, and eventually uh, calculate the speed of light. And there's a wonderful derivation how the c, which is the speed of light, is inversely proportional to square root of permittivity and permeability in free space. So, so that forms the crux of that law that we know later on all the scientists used, including Einstein. Uh, and this unification of electricity and light revolutionized physics, because now one of them is the polarization aspect. The uh, the orientation of electric field affects how the waves interact with materials. So we could study the properties of materials based on characterize the materials based on this property. What is the structure inside the material? We can actually peer into the structure of the material, including crystal structures and other things, based on this polarization aspect. Electromagnetics can be linearly polarized, circularly polarized, electrically polarized. So there's a wide variety of polarization possible, including lasers and things like that. Propagation to different media. For example, we know that it can propagate to air, water, glass, and the refractive index it shows that, and refraction and reflection and transmission, and there's opacity, there's transparency, all that we can figure out based on that. They use specific rules based on Maxwell equations. So applications are many, and we continue to increase. And for example, radio waves, microwaves, optics, antennas, that we use antennas form the fundamental basis of any communication system and communication systems as well as separately. They also help in continuously help in the design electric circuits that we know that micro and other aspects, computers that we use, and the one I am using now, everything is based on that. Transformers to convert powers to under transmit power. And again, I went to the previous one, how the step up transformers, step down transformers, uh, they're all designed based on that because we want to reduce the amount of heat loss in the transmission. So all these can be designed based on that, based on these equations. Electromagnetic devices, including diodes and triodes and all that system that's used, and also all of the machines, uh, big and small, they all utilize this. So they form the crux for the radio and TV broadcasting, where it involves signals, antennas, signals, and other aspects. They use extensively Maxwell equations. Optical fibers, the guiding light, based on the magnetic principle. So now optical fibers supposed to be more efficient than other types of uh, transfers, like electric wires, things like that. So optical fibers are becoming more popular in communications. Microwave ovens that we use a lot, X-ray machines, radar systems, they all depend on electromagnetic radiation principle that is developed from Maxwell equations. So they are immense. We briefly touch upon, and it's very important at paying more attention. That's one of the reasons we are going back to the history of physics, uh, the backbone of the history of physics, which is the conservation laws. So we know the first law of thermodynamics, so far as we know, in our part of the universe, is followed. So there is no problem in energy conservation. But what happens with the momentum conservation? Momentum conservation requires the total momentum of isolated system remains constant unless acted up by external forces. This also kind of follows from the Newtonian laws, the three laws that you know, uh, the first, second law said that the force, everything keeps moving unless it's acted up by external forces. So there's no force; it'll keep maintaining the same system because of the inertia aspects. So the momentum itself is the equation for the momentum is mass and velocity. So P, which is the momentum, equal to mass, which is m times v, the velocity. That's a simple definition. And as we know, later on, this was picked up by people that momentum should be expressed. So Lagrange, for example, p square over 2m plus the minus the potential energy, whereas the Hamiltonian is the p square over 2m plus the potential energy. So p square over 2m is the kinetic energy. So the of moving. So that's the momentum. P is the momentum. The Maxwell equations and momentum. So Maxwell equations describe behavior electromagnetic fields in space. So what happens in space? So the whole thing, is described in Maxwell equation. That's the beauty of Maxwell equation. Uh, we know that that just means what happens inside a surface, inside a volume, what happens. All these are described by these equations, but they don't address directly the momentum conservation. Uh, However, they do give framework for understanding electromagnetic phenomena. So, what are the indirect connections? Electromagnetic waves, such as light, interact with matter. They carry momentum, right? Uh, the wave carry momentum, and later on, we'll see that it was picked up later on as waves and particles, coming together. But the waves itself carry momentum, uh, and then interact with matter, then transfers the momentum. So momentum of electromagnetic waves proportional to the energy that it has, and inversely proportional to speed of light. So when light is absorbed or reflected, momentum is transferred, okay, from the wave to the matter, uh, the material on the surface, especially. So these are studied in greater detail. I am not going to go into details, but that helps to understand something called the radiation pressure, which was predicted from Maxwell equation because of the momentum that's carried by the electromagnetic waves. So the force is, exerted on the surface due to transfer of momentum. And this aspect is used for solar sails and laser propulsion, for example. So there is a pressure involved in that, and the pressure transfer tells us how that is happening. And of course, we know about solar energy conversions, things like that, solar cells, things like that. The overall implication is that while the Maxwell equation do not explicitly address momentum currents, that's a very important point we should note. While the first law that makes very clear about the energy conservation, the momentum conservation is still a question still to be answered. And however, the Maxwell equation says that momentum transfer occurs. So that is electromagnetic interaction. That is something that is, in place of the actual momentum conservation. This will serve as the closest way to understand about uh, conservation of momentum. So these two are important. As we know, if you have simultaneous equations, you have to have two equations. One is the energy, but there has to be one more equation as we solve. I'm going to details about how that is happening. But as physicists, if we try to calculate, usually we have more than one variable, we have two variables. So we need two equations. One equation is provided by the energy. So there has to be one more equation. That equation has to be momentum. And a class physics also talks about conservation of angular momentum, for example, precision, and that's using Thomas precision, things like that. But we'll see later on the charges have radiation problem, and hence the rotational, momentum conservation is questionable. In any case, as far as we are concerned for this episode, the excerpts of the thermodynamics and Maxwell equations based on the classical physics, thermodynamics had given a lot of quantified equations. For example, entropy, we can say delta S is the heat Q over the absolute temperature. It's very important. Absolute temperature is, for example, if you measure temperature in terms of degrees centigrade, you have to add 273 because it's called the Kelvin temperature. So that's absolute temperature. And there is a detailed study of why that happened. And for ideal gas law, for example, we need that PV, which is pressure times the volume, is number of molecules R, which is called the gas constant, and also times P, which is again absolute temperature. Carnot cycle engine, the efficiency of the Carnot cycle engine is based on 1 minus P, the absolute temperature of the cold or the sink, over absolute temperature of the hot object, which is the source of heat. So if we calculate that, we can prove that in order to get 100% efficiency, we have to have the T cold, which is the sink, has to be absolute zero temperature, which is not possible in real systems. So the efficiency will be less than 100%, less than 1, which means that it will be less than 100% to convert to percentage. Uh, the extensive use, another one big equation is thermochemical physics, is the Clausius-Clapeyron equation, which describes the partial pressure ln of P is proportional to RT. We mentioned the temperature over the enthalpy of the vapor. Delta H is the enthalpy plus a constant. And then we can calculate the logarithm of P1 over P2, the vapor pressures, the partial vapor pressures, is directly connected to the enthalpy of the vapor over R and the difference in temperatures. Again, I'm going to detail about the or mathematics of it, but essentially the point out that they help to quantify the phase transition and predict vapor pressure under varying conditions, like in meteorology, like I mentioned, cloud formation, formation of storms, thunderstorms, and hurricanes, and other things, as well as you have the forming rain, what type of cloud will form rain, and also maybe even this, you know, destabilizing systems like in sea, vortexes, and tsunami, different things. So these kinds of phenomena can be studied. Weather conditions and also climatic conditions can be studied using these thermodynamics. They qualify as well as quantify heat, energy, heat, and work in physical systems. Uh, the conservation of energy forms a fundamental basis that energy can be created or destroyed. It can only change forms. Like, for example, you have different forms. Higher forms are called, like electromagnetic uh, forms are called higher forms. And the heat itself is one of the lowest forms. So that everything converts because of entropy. Second law, it keeps converting to heat. That's why the entropy keeps increasing. And so that's something that is, you know, the heat, depth, and things like that were predicted with thermodynamics, which is a harsh form of that the universe might end, things like that. But realistically, a universe may be operating feel like a perpetual motion machine. So that those are being studied now. We still have to understand a lot um, based on black holes, other things, vacuum, and different aspects of the phases of the universe. So essentially, the harmonic functions, potentials, and laws describe how energy behaves in various processes. So the potential forms fundamental basis. We know the chemical potential. Mechanical, each one is described by a potential. The electromagnetic potential, the chemical potential. So each one, or electric potential, even magnetic potential. So they help to relate them and how energy behaves in various processes. Energy, temperature, and heat transfer famous law. Mostly it is static mechanics, I would say, thermodynamics. Then we have kinetics to study how exactly the systems behave in dynamic situations. Okay. Then we have Maxwell equation, which is essentially electromagnetism. And they describe the behavior of electromagnetic fields. He could unify the electricity magnetism and predict electromagnetic waves as well as, and he proved that that is light. He used Gauss's law, Faraday's law, and Ampere's law. He put them together and made these four equations. And energy and momentum are conserved. Like I say, you should read that momentum is a restricted form. Only momentum transfer is conserved, really. Uh, but energy of a closed system is, and total energy is entirely conserved. So the classical physics, so this winds the topic of classical physics, and then we move on to episode 3 about the structure of the atom, and we move on what happened with the classical physics. The classical physics started with Newtonian, Galileo, Newton, and now we have uh, Maxwell, Carnot, all these people uh, were the fundamental people, Emmanouil, Kelvin, and many other scientists. And thermodynamics, essentially, we know that many other scientists we are not known. So they are anonymous. They worked anonymously. They could be priests and other people who didn't uh, market themselves in that sense, or they didn't put their names there. But there are a lot of people involved in that behind the scenes. Then electromagnetism, thermodynamics, they all form the basis of classical physics. Uh, we know the precision of a top, things like that, which then mechanics that understand how the geodesics, like Earth, will behave, and Earth can spin itself. Think that the spin of Earth, large systems, as well as small systems, like later on electrons, things like that, how the spin, all these aspects were described by the use of mechanics, the classical mechanics. So they provide a foundation for understanding the physical world. So we started understanding physical world. We could really understand not only qualitatively but quantitatively how they all bring together. But a lot of questions also came up uh, based on that. So then quantum mechanics that we'll see later on, and relativity uh, came up because of the shortcomings of the classical physics. Some of the things we couldn't explain, but nevertheless, classical physics remains essential, and many people now, develop modified Newtonian dynamics, things like that. That certain gaps in the classical physics we can explain. We can actually, uh, you know, understand quantum mechanics from that point of view, classical mechanics point of view, and essentially you need to just correct some of them. And some people believe in that, but that's an ongoing research that we are also involved in. So thank you very much. This is just I just want to cover a gist of the classical, but this forms the crux, the main aspect of classical. You will see that, which I didn't put it here, that to take care of the conservation, Maxwell came with the idea of fields. So we see that the energy and then the force, which is differential of the space, space differential of energy. How the energy changes. When it moves across space. So that gradient is the force, and then the force itself is not constant, and in the universe, and there is it's changing, even gravity, things like that. So again, so you have to take the gradient of that. This is a conservation law, and the gauge theories eventually developed from these aspects more further. So when you take the gradient differential of space, again, that becomes the field. But the field aspect now is the unification of the field became main thing. But is it the energy field? Sometimes people talk about, sometimes they talk about force field. So those are things we have to watch out for. But the field as concept is very important. Einstein had questioned about that also. Spooky action as a distance. The fields, can they interact from one to another? Quantum mechanics says that a field here can communicate with a field way up there directly. Quantum superposition, things like that. So those are the things that developed, because we could not prove the momentum conservation, although energy conservation could be proved completely. So that's a field that's wide open for research. So thank you very much. And so I'll open now to open discussions. Thank you.
Thanks very much, Rajan. That was interesting.
Thank you.
So, yeah, there's quite a lot in there. I like the way you're tying it in with... What? I was just going to say, I like the way... Oh, yeah.
Oh,
well,
okay. Thank you.
I don't know if you want to... do you have a website or anything that you want to put up, like, or your research case page or anything? So that's up to you.
Okay. Specifically related to this, this I just compendium of things. I put them together, but now we have research separately of each of the papers, that we have done, that I have done. I think I want to compile the list of eventually, list of publications, and then make a book. We can actually make a book that will describe, from starting using these. So this forms very fundamental basis for our reference, because what happens is oftentimes we question, when you are doing research, people also are confused about what Maxwell is saying, what Thermodynamics is saying. That's why I want to look at it separately, irrespective of what is happening now. So this is just the historical things. So you can base on that. That's what they did. And why they did, one of the reasons is, I'm going to episode 3, structure of the atom. They didn't know the formation of electrons and protons and things. These later on, I'm going to research on that. how historically it fitted into this thing. But I don't think they knew about the Dalton's theory probably at that time about atoms. But but Newton has not talked about electrons. I don't think Maxwell has talked about electrons. I have to look into how the electrons, it could have been later on that Rutherford showed about the atom itself consists of particles, charged particles, and that promulgated the quantum mechanics. As we know, that they said that if this charged particle is moving, it is really radiating. So how can you conserve anything? Even rotational, momentum cannot be conserved because the electrons are going around. They are going to radiate, and so there is no conservation there. So then, so that's the problem. So then the quantum mechanics says you have to only describe a probability function, and so on and so forth. And we know what happened later on. Then Einstein came and said that, okay, if it's moving at the speed of light, then the whole mass had to be, the energy has to be absorbed, and the mass had to increase. So again, so the question of the momentum, you see, momentum is mass times velocity, right? So the mass is changing, the velocity is changing, the speed of light is not constant, the distribution, because of the radiation, things like that, the velocity is changing. The m times v, there are two variables, both of the variables are changing. How can the momentum be conserved? Uh, so that's a big question that is still unanswered. Even with standard model, I don't think it's answered. That question of conservation momentum is not answered.
I wonder
Without
that
that,
you could have the time is a variable, yeah?
Yeah. So that's the thing I picked up on. So I'm going to talk, that's what I did more research on time. And I said that time, actually, the real time is both scalar and vector. And how that happens is what I'm studying. And I have I published already some about the rank n tensor aspects. Uh, what is the rank of the tensor? And also in that one, in the recent one OJPS. Should I put that OJPS thing? I don't know. The
Yeah,
website.
if you have any website or ResearchGate or page or something you want to send people to, that'd be a good use screen.
Yeah, I can put this one because it talks about the. Let's see. The one that talks about the recent one. Yeah, let me check. Yeah, this talks about the conservation of, and look into the conservation. I'm looking more into conservation, and I have analyzed about how the vector, the tensor time can be conserved, just like Lagrangian and Hamiltonian. How the conservation law can be pulled out from there. So that is a website I can put that. I think I'll try to put that.
Put in the chat or something?
In the chat. Yeah.
Good idea.
So this chat, when I put, I think it should be for everybody. Let's see.
Yeah, that's for the channel. So
I just briefly say talks about time and conservation. Analyze like the Lagrangian, Hamiltonian actions. So I just briefly mentioned that.
oh, sorry.
Can you see that?
Yeah, that went up.
Yeah.
Two separate comments. Okay, so that's fairly good. I think if people want to comment on the video, they can do so below and share their opinions and questions with Rajan, and then you'll be able to get back to them in time as well. Yeah. So that's pretty good. So and you managed to put up some stuff. So I think we can leave it there, and then we can reconvene next week, where we will do sort of like a live coding session, free form, and it should be good. Okay.
Okay.
See you next week then. So I'll just.
Okay. Thank you very much. Yeah.